Electromotive force is produced when a conductor passes through a magnetic field formed by a magnet. Electromotive force is measured in volts and is commonly referred to as potential difference or voltage. Passing a conductor through a magnetic field induces the electromotive force, thus creating the potential difference to create current flow which can be provided to a load. By connecting a current meter to the conductor, we can measure the amount of current produced by passing the conductor through the magnetic lines of flux. As the conductor passes down through the magnetic lines of flux, it produces a current in one direction, and as it comes back up through the lines of flux, it produces current in the other direction. If the conductor is passed from left to right in the flux lines, no current is read because the conductor does not pass through the field of flux lines. Passing the conductor in a circular motion through the flux lines produces a sinusoidal waveform that corresponds to the location of the conductor. Sinusoidal waveforms are often referred to as a sine wave. Looking at the waveform, we can see how the current changes as we pass through the magnetic lines of flux. Take note that one revolution, or complete circle, creates one complete cycle for the sinusoidal waveform. The alternating current provides power, then no power, and then power again, as the waveform cycles up and down from 0 volts. Electric power is the product of the electromotive force measured in voltage and current measured in ampere. When we evaluate a single waveform, we can see it is not a constant power source. This type of single sinusoidal waveform is known as single-phase power. In the United States, the standard cycle frequency is 60 Hz. This means that the conductor is making 60 revolutions per second. By adding another conductor to the equation, we add another sine wave, also referred to as a phase. By making the second phase 180 degrees apart from the first phase, and with the same voltage, we've created a more constant total power output. However, there are still drops or dips in the combined waveforms, and this still does not provide a good constant power output. By adding a third sine wave or phase and having them equally apart from each other at 120 degrees, there are minimal points in time when the power output is low. This is three-phase power. Because of the need of constant, more efficient power, three-phase power was created and is very common today. Due to its stability and economical advantage, three-phase power will be around for a long time.